What was that, a 50? Is it going? Yeah, it's going. Okay, all right. So, I know you're all excited to put money in that bucket. Well, I'm going to count that money at the end. Take commission.
Sorry, as treasurer of SPS, that is unfortunately private and you're not allowed to hold it. So you can't count. That's my job.
So, our topic for today.
You just can't count. That's why he's a theorist. He doesn't know.
Every minute you waste, I'm going to keep you here. Because I have to get through this. We're on time budget. Okay. We are at that point where we have enough in our background to formally state the content of general relativity. So we're going to state that, and then we're going to talk a little bit about some of the subtleties associated with it, and then end with a connection between general relativity and the theory that it seeks to generalize, which is Newtonian gravity. So in general relativity, we seek to answer two questions. How does space-time get curved? And how do objects behave on curved geometries? Okay, so answering A is where we had something really new. B we've already actually answered, and I'll just pose this as a question to the class. Oh, look, it's Adria again, because she has 2 cards in the stack. Adria, what's the answer to question B?
What, like how do objects behave in curved geometry?
Yes.
Probably in a weird way. Is that what you're thinking?
So what mathematical tool?
Oh, geodesics. Is that
Yes. They follow geodesic trajectories. Okay. So if you have nothing but gravity in the game, then objects follow geodesic trajectories where the geodesic itself reflects the actual geometry, because different geometries have different geodesics. Now we're actually going to elaborate the answer to B a bit more today and talk about, well, what if you have other forces in the game? So we've already seen sort of a hint as to the answer to B, but we're going to complete this in the course of our discussion today. But before we get to the rest of the story for B, we're going to talk about the answer to A. So without any further ado, how do geometries get curved? Well, the mathematical foundation of that is Einstein's equation, or equations, depending on how you count. And Einstein's equation is as follows. It's the Ricci tensor minus 1/2 the space-time metric times the Ricci scalar, and that is equal to 8 pi times the Newton constant g times the energy momentum tensor. Okay? So that is Einstein's field equation for the gravitational field coupled to energy and momentum sources in the form of the energy momentum tensor T mu nu.
Wait, you said the R, just plain R is the Ricci scalar, right?
Yeah, so this is the Ricci tensor, this is the Ricci scalar, both of which are built from the Riemann curvature tensor. Notice the Riemann curvature tensor itself doesn't appear here, but of course you would have to know it in order to construct R mu nu or R. In terms of the way that we think about this equation, it's much like Maxwell's equations. You provide sources, and then you solve the differential equations for the resulting, in this case, geometry, which is encoded in the Ricci tensor and the Ricci scalar. Ultimately, the thing you're solving this for, though, is the metric. The metric is hidden in here, right? The metric is what we use to calculate the Christoffel symbols, and then we use the Christoffel symbols to calculate the Riemann curvature tensor, and then we use the Riemann curvature tensor to calculate the Ricci tensor and the Ricci scalar. So deeply buried in here in a bunch of derivatives in very dense notation, the fundamental unknown is the metric. That's the thing we're solving this set of differential equations for. How many differential equations does this represent? Hunter.
16.
16, okay. Does it really represent 16 independent ones?
12 independent, I think, right? Or is it? No, 10.
10. It's 10 because this is symmetric in the exchange of nu and nu. Symmetric, they all actually need to be symmetric. And that means that while this is ostensibly a 16 4x4 matrix, okay, since it's symmetric, you just get the diagonal and then half of the off diagonals, which makes it 10 independent equations. Okay? Some notation, this quantity right here, the combination of r mu nu minus 1/2 g mu nu r is often abbreviated to capital G mu nu, which is called the Einstein tensor. And I believe there's a call to evaluate the Einstein tensor in the GREAT package. So you can feed the GREAT package a metric, a set of coordinates, and ask it to calculate Einstein. You can, of course, also ask it to calculate the Ricci tensor or the curvature, which is what they call the scalar curvature. And again, all of this represents 10 independent equations. Okay. And the idea here is to solve for the metric. These are, of course, differential equations. It's not obvious when it's written in this form, but again, buried in the r and the r mu nu are derivatives of the metric. So this is a different set of differential equations, highly nonlinear, a couple differential equations. But at the end of the day, if you can manage to solve it, what you want to get for your solution is the metric g mu nu. How many components are there in the metric? How many unknown components are there in a metric? 10, yeah, it's a symmetric 4x4 matrix. So there are 10 unknown functions. And you know what? That seems to agree very well with the fact that we have 10 independent equations in Einstein's equation. Man, it's like it was meant to be, right? Doesn't that sound awesome? Yeah.
So is it due to the fact that there are only 10 unique parts of the metric that you only care about like one part of the Riemann curvature? Like why doesn't the stress energy tensor affect all of the curvature?
So you mean why doesn't, well, the part,
So it only affects the Ricci parts, I guess, right? Only certain components of the Riemann curvature.
I wouldn't say certain components of the Riemann curvature, but rather certain combinations of components. So remember, to get from the Riemann curvature tensor to the Ricci tensor, it's not that you ignore certain components, it's that you add up sets of components.
Yeah.
So all the components come into this, it's just they do so in sums instead of individually. Okay, I mean, individually, if you had the Riemann curvature tensor up here and here, you would be working with 256 equations, which doesn't mean you can't do it. I mean, it means you can't do it, but doesn't mean you shouldn't do it. But no, all the information is there. It's just it's kind of there because it appears in sums. So you have to be a little bit careful. This is just, it's not sensitive, it's not that sensitive to all the features of the geometry. Some of them it doesn't care about, and it's just happy to sum over them. Okay, so ostensibly we have a situation which, at least for Physics 1 students, looks about right. 10 equations, 10 unknowns, but this is not Physics 1. This is general relativity. So it turns out that this is not the entire story. We also have a geometric condition, which sounds a little bit weird to say in this context, but I'll give you an analogy in a few minutes that will make this make more sense. And this geometric condition is called the Bianchi identity. And the Bianchi identity is that the covariant derivative of the Ricci tensor is 1/2 the covariant derivative with a lower index of the Ricci scalar. Okay? And this represents how many independent equations, Benjamin? How many independent equations does this represent?
Oh, 4.
4, because remember, to count the equations, you just count the total number of free indices. The mu is sum, so don't pay attention to it. All the left-hand side has is a row, and row has 4 values. And similarly for the right. So this is 4 independent equations. Okay? So this is 4, and of course they're differential equations because you see derivatives explicitly in this. Okay? So now it seems like we're in trouble. Right? Physics 1 students start sweating because they're like, wait a minute, I have 10 unknowns and 14 equations. Yeah. Tell me about it. But you have to be a little bit careful when you're just counting equations and then comparing it to the number of unknowns. The moral that you kind of learn from algebra context is as many equations as unknowns is well defined. Too many equations is over-constrained. Too few equations is under-constrained. This is a little bit more subtle. So in order to kind of give you an idea, what the Bianchi identity is telling us is that some of the equations that we get from here are not actually independent of each other. So identifying these as 10 completely independent equations is actually incorrect. Let me give you an analogy. It's kind of hard to do it in the guts of this because I don't want to break this thing open. It's already bad enough. But let me give you an analogy. Suppose I gave you a set of 3 differential equations. Say equation 1 for unknown functions f, g, and h. So you just imagine there's some derivatives of f and g and h and maybe factors of f and g and h, and they're in all these combinations and they're equal to something. Okay? And then I gave you another equation involving those same 3 unknown functions, and then yet a third equation involving those 3 unknown functions. Okay? So right now, looking at this, things look good. I've got 3 different equations, 4 involving the same 3 unknown functions, so that looks like a good system. But then I might come along and give you an identity that looks like this. If you were naive, you would go, wait a minute, that's no good because now I've got 4 equations and 3 unknowns. That's overdetermined, right? But actually, what the identity is telling us is that of these 3 equations, I should only use 2 of them. Because if I use E1 and E2, the information in E1 and E2 is already contained in E3. So what the identity actually does is it removes one of these equations. It creates an underdetermined system in this example. So I'm just trying to illustrate to you that just a silly counting of equations doesn't necessarily say you're overdetermined. In fact, the presence of an identity can decrease the number of independent equations. So at the end of the day, and again, it's hard to illustrate this specifically in this case, at the end of the day, I should really say this as equations. At the end of the day, taking the Einstein equation and the Bianchi identity into account leaves me with 6 truly independent equations. Okay? All right, so let me just summarize this here, and then I'm going to So I'm going to show you how this exact same type of story plays out in a context you're more familiar with. Okay. NM. All right. In NM, we'll start with half of Maxwell's equations. Okay. The important part about this first half of Maxwell's equations is that these are the dynamical equations of electromagnetism. These are the equations you can get from varying in action. These equations play the role of Einstein's equation in general relativity. Okay? Colton. Colton, how many independent equations do these represent?
Or wait, no, those are vectors. 6. 9. 10.
How many here?
1.
1. How many here?
9.
3.
3.
Each side is a vector,
Okay, great.
basically.
Yeah.
So this is 3 equations, 1 equation, so it's a total of 4 equations. Okay, this is going to be easier. How many unknowns?
4.
So there's an E and there's a B. How many unknowns?
2.
How many unknown components?
Oh, I see. That'd be 6.
6. Good, good. We'll get you there. We'll always get you there. Okay, so again, you supply J and rho. You don't, I mean, look, it's a philosophical thing. Like, I could just give you these differential equations and say, here's E and B, find J and rho. But that's not the way physics works. You provide the sources and then solve the equations for the fields. That's the way this is meant to go. Okay? So J and rho are given, and then E and B are the unknowns, and of course they each have 3 components for a total of 6. Okay? So this counting doesn't look great. But then we also have the other half of Maxwell's equations. Which represent 4 more equations. And these are geometrical equations. They do not come from any kind of action principle. These are the Euler-Lagrange equations of motion for the electromagnetic field. These are not Euler-Lagrange equations. These are analogous to the Bianchi identity in general relativity. Did you learn that in your E&M class?
No, but you told us that on the first day.
Yeah, I know. I do that. They do that. Okay. All right. So if you look at this, it kind of looks bad because at the end of the day, we've got 8 equations for 6 unknowns. Okay, so it seems over-constrained. You've worked with E&M before. You've worked with these equations before. Maybe you've looked at them more in their integral form, but they're different forms that are changing. But here's the way this usually gets resolved. First of all, what you do is you take these equations, the geometric conditions, and you say, actually, based on these relationships, I can create the electric field as the gradient of a scalar field, and I can create the magnetic field as the curl of a vector field. And so secretly, the electric field I can get from a single piece of information. That's the scalar field, phi. The magnetic field I get from a vector piece of information, A. But at the end of the day, I'm actually looking for 3 unknowns. And then I come back up here and say, okay, now I've used these equations to establish that I can write E and B in terms of these potentials, leaving me with 3 unknowns. And now I come back up to these 4 equations, and I try and use those 4 equations to find these 3 unknowns, which still seems bad. Okay, still seems overdetermined. But there's an interesting observation that you can make, which I don't know, this is probably pointed out in your E&M class. If we take these expressions, maybe I can do this right here, then we can consider the following. We can consider del dot del cross B. Okay, so I'm going to del dot this second equation. If I del dot that second equation, I have del dot J plus, and then I'm going to swap the del with the partial derivative with respect to time. Okay?
Okay, Alex,
Yeah.
how is that only 3 unknowns? Don't you have phi and then 3 components of A?
Oh, sorry. I'm sorry. You're totally right. You're totally right. And I was actually getting secretly nervous because I was like, shit, that counting is off. You're right. It's 4 unknowns. You're totally right. Thank you for that. So you have 4 unknowns, 4 equations. Things look great. But now I'm going to show you a problem. Okay. So I'm del dotting the second equation here. I got this guy right here. Del dot, the curl of something is automatically 0. Okay, so this guy is 0. And I can use the continuity equation, which says that del dot J plus partial rho partial T is equal to 0. That's just the charge conservation equation. This is the statement of the conservation of electric charge. And I can use that to replace this guy with minus partial rho partial T. And so at the end of the day, this is going to tell me that partial T of del dot E minus rho equals 0. Okay? Okay, so watch this. So the first of Maxwell's equations is just del dot E minus rho equals 0. But from the second Maxwell equation, so I only use this one, from the second Maxwell equation, I can arrive at the conclusion that the time derivative of del dot E minus rho equals 0. What that means is at the very beginning of whatever I'm studying, if I say that this equation is true, then it's forced to remain true for the rest of the time that the system evolves. So there's a sense in which by fixing the initial conditions, you can eliminate the first of the Maxwell equations from governing the dynamics. It's automatically enforced by the second one. Okay? Now, what I'm trying to get at, which I'll say now, is even though it looked like you had a perfect matching of 4 unknowns with 4 equations to solve them, in truth, one of these equations is not really as dynamical. So in E&M, you actually have a slight underdetermination. At the end of the day, for E&M, you have 4 unknowns with 3 equations that you can use to find them. You are actually trying to solve an underdetermined system of differential equations. Okay? Which is completely what you should expect. Why should you expect that? Exactly. There's a reason why I picked Gage to answer that. Let's look at what you're trying to find. You're trying to find this thing. You're trying to find the 4 vector, A mu, which has essentially the scalar potential as the time-like component and then the magnetic vector potential as the spatial components. Okay? But the one thing you know about electromagnetism is that it is invariant under a gauge transformation, where the gauge, and maybe I should pick a different symbol here. where you can subtract from the vector potential A mu any derivative of a scalar function. And this will not change the physical content of E&M. That is in line with this statement, because if we had 4 equations and 4 unknowns, that means there would be one unique solution for A. For this A and this phi, there would be one unique solution. But gauge invariance tells you, no, there can't be a unique solution, because you can always change the solution by exactly 1 degree of freedom. That's choosing this function theta. Okay? Do you all feel comfortable with that from E&M? Because I'm about to take it right back to GR. How do I read that face? Like, what do I do with that?
You think this is like a comfortable thing?
No, I don't.
That was just
So, how many of you remember that E&M has this gauge invariance?
I remember.
Okay, I mean, you should take particle physics, because I'll teach you that E&M is nothing but a theory of gauge invariance. But anyway, E&M has this built-in gauge invariance. The potentials are only defined up to this transformation. There's not a unique solution for what's the potential. There's a unique solution for what's the E and B fields, but not the potentials. In fact, that's how you kind of discover gauge invariance in your E&M class. You say, oh, we can build E and B from these potentials, but if we change the potentials in this way, we still get the same solutions for E and B. Okay? All I'm pointing out is that this gauge invariance of the potentials is completely compatible with the fact that in terms of potentials, we have four unknowns and 3 equations. It's underdetermined by exactly 1 degree of freedom. Okay? Now coming back to GR. At the end of the day, we have 6 independent differential equations and we have 10 unknown functions. So even if we use all 6 of these equations and we solve those equations and we get a metric, how many degrees of freedom are we still going to be left to mess around with? 4. So you can solve this to get a metric with 4 degrees of freedom to tweak. What are those 4 degrees of freedom?
Space-time?
Space-time what?
Continue.
Translation.
Don't say continuum in this class. It's like you started out with quantum and then we somehow managed to move to the continuum. So I never say space-time continuum.
Is it the connections?
No. It's the coordinates.
Oh.
You literally can, if you solve for the metric, you've solved these equations, but then you are free to change coordinates, and it will change the way the metric looks. But just because you change coordinates doesn't mean you're changing the geometry. Coordinates are not like, they're not real. Like, look around. I don't see any coordinates. So if you solve these equations for a specific form of the metric, you're always going to have the flexibility to change the coordinates. And that will change the form of this. And you have exactly 4 coordinates you can redefine. So the fact that you have these 4 degrees of freedom left over is a good thing, and it's something to be expected. And in fact, in perfect analogy to E&M, this is the gauge freedom of general relativity. It is the freedom to redefine coordinates. Okay. All right. Any questions before I? Oh yes. It's like, wow.
So are we saying the metric is analogous to the E and B fields?
No,
Okay.
we're saying the metric is analogous to the potentials
Okay.
because you have a freedom to redefine it.
Oh, so we can change. I thought
You
the-
can
I
change,
thought the metric
you've got to be
was-
careful. There is a geometry, but that geometry can be described by different forms of the metric depending on the coordinates you pick. And you know this, I've told this to you a million times. That's a geometry, and you can use coordinates where the metric looks like this, or you can use coordinates where the metric looks like this.
Oh, okay.
These are describing the same geometry, They're just using different coordinates. So you can't look at the metric and say the metric uniquely defines the geometry, because many different metrics can describe the same geometry. And it's exactly that coordinate redefinition freedom that connects them. Mike?
So in this degree of freedom, the degrees of freedom, are we changing like how like the specific coordinate system like relates like to the other like
Well, what you do is you solve these equations in some coordinates, because you want to write down a metric, so you got to have some coordinates in mind. So you pick a set of coordinates, you solve the equations in those coordinates, and you'll get a solution. But then you are always free to then switch to a different set of coordinates.
okay.
Does that make sense?
So like we can go from like the x, y to like spherical coordinate system, and that would, I guess that makes
And that doesn't change the geometry.
right.
It only changes our description
But
of
you're
the
not like
geometry.
changing the location, just like the origin, basically.
Yeah. So the geometry that I'm alluding to, this thing that is actually physical, that gets unchanged if you change coordinates, is analogous to E and B. These are physical. No gauge transformation can change E and B, because you can go measure those. Okay? All right, so other questions before I zip right along?
Will this concept be on the test?
No, this will not be on the test. It'll be on the final.
Yeah, yeah.
It will definitely be on the final, but it will not be on your test on Tuesday. Okay, so I say all this, and part of what you have to understand, and you have to understand it. I'm going to say it, and then you have to understand it. The entire course is about to shift gears, because we have spent the entire semester so far developing the Einstein equation, like what does all that crap mean, and the geodesic equation. From here on out, we're less interested in the formalism of where those equations came from. Our attention is going to be on solving them, and worse still, because general relativity is tough, even once you have a solution, interpreting what that solution means gets really weird and can be hard. But our entire focus of the course is now on taking these equations and solving them and giving interpretations to the solutions. We're done building up the formalism. Okay? So that's why I'm spending the time I'm spending on trying to, do counting of equations and determinations of them. Okay, so I said that I was going to flesh out the answer to the second question. How does physics change, and I'm slightly rewording it, change on curved spaces? Because now I'm interested not just in how do you describe the gravitational influence on a curved space, but how does, for example, electromagnetism change on a curved space? And it turns out that the answer to this is pretty succinct. It uses what we call a minimal coupling prescription. Which is where you are going to see the payoff from having spent so friggin' long doing special relativity. Okay? So here's the recipe. Start with a law. This is any physical law you care to think about. In an inertial frame, in flat space. That's, of course, the domain of special relativity. So any equation that we wrote down in special relativity, as long as we're working in rectangular x, y, z, t coordinates, don't do this with spherical coordinates because it won't work. So in an inertial frame in flat space, write down any physical law you care to write down. Write the law in terms of true 4D tensors, okay? We spent a lot of time defining what tensors were, identifying when something was and wasn't a tensor, being really careful because there are some things that you think is a tensor because it's got indices, but it turns out not to be. So make sure that whatever law you're picking on, you write in terms of tensors. Now, what do I mean by that? You might write down Newton's second law, but Newton's second law itself is not written in terms of tensors. It's written in terms of F and A. Those are three-dimensional vectors. You want to write Newton's second law in terms of four-dimensional tensors, which you can do. Okay, we haven't done that, but you can do it. And then here's the best part. I love this. Assert that the same equation is true in curved space. So you can literally get the form of your equations entirely in terms of the context of special relativity. And if you're very careful to write them in terms of tensors, then you can just say, and it's also true in curved space. Now that might seem like more than you should swallow, and I'll give you a couple of concrete examples, but let me first tell you how this in practice works out. So, start with a Lorentz invariant theory in terms of tensors. Okay, that's making sure you're doing step 2, and then if you're working in an inertial reference frame, then you know you've got a Lorentz invariant theory. It's an inertial reference frame in Minkowski space. And then when you go to curved space, of course, you don't use the metric of flat space if you're in curved space because it's not going to have the same metric. So what you do is you take your equation and everywhere you see the metric of Minkowski space, that's the metric that's going to appear in 1 and 2 here or step 1 here. You replace it with the metric of whatever curved space you're interested in doing physics on. But there's one more place where the metric appears in many physics equations, even though we don't necessarily write it explicitly, and Chance is going to remind us. Where does the metric sneak in physics equations, making them more complicated than we otherwise think they might ought to be? We had to redefine something.
Derivatives?
Yeah, derivatives. So the ordinary derivative, partial mu, okay, that's not a good tensor derivative. So we have to replace that with the covariant derivative. Okay? So you do this everywhere, and that's what your theory looks like on curved space. So let me give you a couple of examples. And it really is that easy. So let's start with our favorite example. I swear, I think I should lobby for you guys to get credit for advanced E&M having taken this course.
That would be incredible.
That'd be incredible. Okay.
Yeah, we've already taken it.
Okay. So let's start with the tensorial form of Maxwell's equations. Okay, I wrote Maxwell's equations up here earlier. Were those in four-dimensional tensor form? No, you saw E vector, B vector. We need these in four-dimensional tensor form. Okay, we've seen these earlier in the course, but we have the two dynamical equations which collapse into partial mu F mu nu equals J nu. Okay, this is the four-vector source, which the time-like piece is the charge density rho, and then the rest of it is the vector current. And then we have the Bianchi identity, which was written like that. Okay, and you proved that this expression gave you the corresponding spatial versions of Maxwell's equations in a homework assignment, where F mu nu was defined from the upper F mu nu with factors of the metric. You can go either way, it doesn't matter. And that is definitely not right. Okay? Here we go. To write down Maxwell's equations in curved space, right? We have done step one. We have written down a Lorentz invariant version of Maxwell's equations in terms of tensors. And now all we do is make these replacements. And that's it. That is electromagnetism on the curved space. Obviously, electromagnetism on a curved space is more complicated than electromagnetism in flat space. I'm not going to argue with you about that. The complication, though, is not in the form. The form of the equations is identical. Where it gets complicated is that that derivative is now that derivative, and that derivative sucks. And this metric, which is just good old minus 1, 1, 1, 1, 1, it might have been too many ones, is now replaced by this metric, which in general can depend on position in space and time. But nonetheless, the overall form looks the same. Yes, ma'am?
Your indices on that F over there, I think are...
Yeah, they're screwed up. They're always
Just change
screwed
the
up.
mu with the mu.
Oh, it's this. I'm trying to be consistent. That's F nu lambda.
Yeah.
Oh man, it's like everywhere. It's so bad.
Also higher.
Also, yep, up above, the other F one. Right above the arrow. Yep.
Yeah.
And then move your finger a little bit to the
Oh my gosh, it's so awful. Yeah, there you go. I'm a F mu nu kind of. I love me some F mu nu, and I do not like to get away from F mu nu.
Yeah.
Anyway, all right. So does this process make sense? Because I'm about to give you one more example.
Can we use for like any law? Like
Any law that's valid in flat space.
wow.
So let me give you another example, which is actually really cool.
Do the ideal gas
Good luck phrasing the ideal gas law in terms of tensors and four dimensions, but go for it. I'm sure you can do it. Okay. In flat space-time, granted with no gravity, because flat space-time has no gravity, free particles move along what kind of trajectory? Straight line. So the path of a particle looks like this. All right? Of course, you all recognize that this is, of course, just saying that the acceleration is 0, which is what you know describes the behavior of a free particle in flat space time. I'm, of course, writing this as a 4 vector because it needs to be written in terms of 4-dimensional tensors. Another way to write this is breaking up the directional second derivative. So peeling off one of them, we can write it like this. Okay, I'm just using that standard breakup of the directional derivative. I can write as dx mu d lambda partial x mu, or in this case nu nu. Okay. And now to make this true in curved space, all we do is we replace metric factors with curved metrics. There are no metrics in here. And derivatives with covariant derivatives. What is that? That's the geodesic equation. So the geodesic equation actually follows from this minimal coupling prescription. You just say, what is a particle in empty space-time with no gravitational effects and no other forces acting on it? How does it behave? It behaves like this. The geodesic equation. Okay. So, yes, your final report will be to apply this minimal coupling prescription to the ideal gas law, and we will all be excited to hear about the results. Are there any questions before we move on? Okay, what I'm about to do is going to hurt a little bit, but it's important. I seriously debated skipping it, but it gives us a particular result which we use later on, and I think it's also a very important thing for you to see to connect general relativity to the theory of gravity that you are very familiar with, and that's Newtonian gravity. And I always come to this lecture wishing I had a hat. Well, not like a Waldo hat. Where's Waldo? Where's Newton? And to put your hat on. First of all, I'm not going to put your hat on. Secondly, that is an inappropriate hat for this topic. But thanks for the offer. Thanks for the offer. Okay, I was thinking about where's Waldo. But anyway, where's Newton? So in general relativity is a generalization of Newtonian gravity. That means that there should be some sense in which we can take some limits and get back Newtonian gravity. In the same way that special relativity generalizes Galilean relativity, the relativity that you're used to from mechanics, and you can take a limit of special relativity, that is, take the speed of light to infinity, and you'll reduce yourself back to Galilean relativity. Okay? So what we want to do is take general relativity, and we want to find Newtonian mechanics out of it. So we've got our two starting points. That tells us how sources curve space-time. And then we've got the geodesic equation, which I'm going to write in this form, explicitly putting in the Christoffel coefficients. Which tells us how gravity influences the behavior of things. I'm not going to worry about other forces because I just want to try and get Newtonian gravity out of the story. So what I want to do is I want to beat this into the relevant Newtonian equation, and beat this into the relevant Newtonian equation, and I can go ahead and tell you what the relevant equations would be. These are going to look a little bit different than what you're used to. So Einstein's equation should tell us how a Newtonian gravitational field is created from mass. Now remember, in Newtonian gravity, mass is the only thing that gives rise to gravitational forces. You don't get gravity from energy or momentum in Newtonian gravity. It's just the mass. Okay? Of course, the gravitational field can be derived from a gravitational potential, kind of the same way that you derive the electric field from an electric potential. So the equation that we're trying to reproduce should look astonishingly like an equation from E&M. Grad squared of the gravitational potential phi, from which we can get the gravitational field, is 4 pi g times the mass density rho. Okay? This is the equation we would like to somehow find here. It's an equation that tells us how sources give rise to the gravitational field in this description. Here it's how sources give rise to curvature. And then in the second case, We basically want to get Newton's law with gravity being the only force out of it. But if gravity is the only force and you plug it into Newton's law, you know what the result is. But this is just minus grad phi. Okay, so what you're trying to get out of this is that A is minus grad phi. That's equivalent to saying I'm using Newton's second law with gravity being the only force. Okay, we good? All right, here we go. So we're going to need some limits. We need limits. So first of all, as you might anticipate, Newtonian gravity is typically a non-relativistic context, so we're going to need non-relativistic limit, or we're going to need a small velocity limit. I shouldn't say non-relativistic because which relativity am I talking about? So we'll say small velocity limit. That means that the spatial components of the velocity defined with respect to t, or sorry, the spatial displacements with respect to coordinate time, this is literally vi, should be much less than c. But in this class, c happens to take the magical value of, Will? 1. Good. So that's 1. And now I'll just do a little maneuvering. If dxi over dt is much, much less than 1, then that tells me that dxi is much, much less than dt. Okay? Alternatively, dxi d tau is much, much less than dt d tau, which is, of course, just dx0 d tau. And the reason I'm doing this, I know you're like, why is he doing that? The reason I'm doing this is because in general relativity, everything starts off as 4 component things. Or every index takes 4 components. So if I'm going to tell you about a small velocity limit, I need to tell you about what's happening to the spatial components of the 4 velocity in comparison to the time-like component of the 4 velocity. These are components of the 4 velocity. They're derivatives of the coordinates with respect to proper time tau. Okay? So this is just saying that in the limit of small spatial velocities, the time-like piece of the 4 velocity is hella big compared to the spatial pieces. Okay? So when we write down a 4 velocity vector, we can largely focus on the time-like piece. Or more, if we like take quadratics of them, then we can ignore quadratics and the spatial velocity components because the time-like piece is bigger. Okay, there's another limit, and that is that we should expect a weak gravitational field. And a weak gravitational field we can write in terms of an expansion above flat space. So we've got the flat space metric plus a small fluctuation where the magnitude of this thing is small. And the moral here is that we will ignore terms of order h squared and higher. So that's the advantage of taking a weak field approximation. A weak field approximation is something you might expect because if general relativity is a correction to Newtonian gravity in extreme circumstances, well, one extreme circumstance is when you get really, really highly curved geometries, but that corresponds to really high deviations from flat space. Even outside of a planet, the deviation from flat space is, if you're far away from the planet, the deviation from flat space is really not big. You might say, oh wait, that's a whole star creating a gravitational field. Well, if you're far enough away to be like on the Earth, orbiting the sun, the deviation from flat space is really not that big. You can, of course, get really big deviations if you go, for example, into black holes, or if you go really, really close to the surface of a star. But if you go close to the surface of a star, you've got other problems. So. And then lastly, sadly for Gabriel, we are going to assume a static gravitational field, so we can ignore gravitomagnetic effects. because Newtonian gravity is normally formulated without them. And what that means is that we're going to take the time derivative of the metric anywhere we see it to be 0. So we're just looking at static gravitational fields. Okay? Now, I'm not going to prove this. I proved it in the notes. It's just a bunch of index manipulations. But one consequence of B, and I'll do this. Another consequence of B is that the inverse metric takes a weird form. Okay, the inverse metric, g mu nu, is just the inverse of this thing, but we want to write the inverse metric in terms of these or their inverses. And I'm just going to write what the answer is. It turns out to be kind of weird. It's eta inverse minus eta inverse h. Okay? And in the notes, I just have a little demonstration of why the inverse has to look like this if the original metric is going to be broken up like this. Okay? You can actually prove it to yourself because all you're doing is saying that you want g nu alpha to be equal to delta mu alpha. And this is the form that you need if you want to combine it with that and get the delta function. That is, you want these two to be inverses. That's what that means. Okay, but that's in the notes. It's just a little bit of index manipulation. It's nothing insightful. Okay, so we're going to start by looking for this equation. So we're going to start with B first, and then we'll do A second. So consider a massive particle. Why would we only consider a massive particle? Don't make me draw this card. Avery, why would we only consider a massive particle if we're trying to take the Newtonian limit?
So we're working with gravity.
So gravity doesn't affect massless particles?
Oh, no, it does.
It does.
Yeah.
So why are we taking a massive particle in particular? Danielle?
Does Newton's laws work with mass as a source?
Because we want to get Newtonian gravity out of this, and Newtonian gravity only cares about massive particles. So you were saying the right thing. You were using gravity without any qualifiers. I was like, I don't know what Avery means when he says gravity. Okay, so here we go. I'm going to consider a massive particle with tau being the proper time. And let's do it. Okay, here we go. D2. So I'm going to get it from the geodesic equation. So I'm just replacing the parameter. So this works for any parameterization lambda. I'm just now choosing my parameterization to be proper time tau, where remember tau is the square root of minus ds squared. That's what proper time is. But you have to identify that it's a massive particle because then you realize ds squared is negative, and then you can put the negative in, fix the root. It's not going to matter very much for what I'm about to do. Well, it might matter. We'll see. I don't know. Okay. All right. Finishing this up. And I know I'm going fast, but man, I got 2 pages of dense notes to get through, and I really want to finish this before. It's all about trying to get us in a good place before spring break, because I don't want to get halfway through something and then send you away for spring break. Okay, so I've just rewritten the geodesic equation in terms of a parameterization of tau. And now we're going to use a couple of our observations. We still got d2x mu d tau squared. When I do this sum, I'm summing over the Christoffel symbols times quadratic in the components of 4 velocities. This is a component of the 4 velocity, this is a component of the 4 velocity, okay? Which components of the 4 velocity are going to dominate this term? Yeah, the dx0 d taus, especially because they're quadratic, or especially for the quadratic case. So when I do that summation, I can ignore any of the summation terms where rho or sigma is spatial. So that means that I effectively reduce this to 0, 0, dx0 d tau, dx0 d tau. Okay? So that's using condition B. But now let's dig a little bit into the meat of what gamma mu 0, 0 is, using the definition of the Christoffel symbols. Okay. Daniel, what is this term?
0.
0.
Also 0.
Good. So we've got these two things are 0. How do you know that?
They're time derivatives of that metric.
Yeah, exactly. That's using condition C. Okay. So this actually looks like it reduces really nicely, except that the inverse metric is ugly. Okay, so let's write this out. So this becomes minus 1/2 eta mu lambda minus eta mu alpha eta lambda beta h alpha beta d lambda. Okay, G00 is just eta 00 plus h00. And what is the derivative of eta 00? Don't make me draw this card. Say it again?
0.
Yeah, what is eta 00? Is -1. This is the 0, 0 component of the metric of flat space in Cartesian coordinates. This is -1, the derivative of it vanishes. So I can replace the d lambda G00 with d lambda H00. Okay? And then I'm actually going to provide one more condition. Yeah, one more condition. So in addition to assuming that h mu nu is small in magnitude, I'm also going to assume that it's slowly varying. So we can ignore terms which are higher than quadratic and derivatives of the metric fluctuations. Or I can ignore terms which are products of the metric fluctuation and the derivative of the metric fluctuation, which is exactly what this term is. Okay, it's the metric fluctuation times the derivative of the metric fluctuation. I'm going to ignore that, and this entire thing reduces to minus 1/2 eta mu lambda d lambda H00. Okay, so that's my Christoffel symbol with the two lower indices being 0, 0. Plugging this back into the geodesic equation, we've got d2 x mu d tau squared minus 1/2 eta mu lambda d lambda H00 times dx0 d tau d squared equals 0. How many equations does this represent? How many different equations does this represent? 4. It's got one overall index mu. So mu takes 4 values, so this is 4 equations. And at this point, we can consider different values of mu. Now, we can consider the time value and then one of the spatial values. We don't have to do all the spatial ones because they're all going to look the same. So if we do the mu equals 0 version of this, the mu equals 0 version of this becomes d2 x0 is just time. Okay? Now, really important, what I'm pointing at requires lambda to be what for this to be non-zero? Lambda has to be 0 because the metric eta is diagonal and the inverse metric eta is diagonal. So it's only non-zero when the indices are the same. So that means that lambda is 0. But if lambda is 0 here, lambda is 0 there, and so what's this term? It's 0 because of condition C. Okay? So this entire term vanishes, which means that the second derivative of t with respect to tau squared is 0.
I thought h00 could vary slowly.
No. The derivative with respect to time of anything is identically 0 in the static case. Yeah. Okay? All that this is saying is that time is a perfectly good parameterization. T and tau are linearly related at worst. In general relativity, we have to be really careful and stay away from using time because time can get transformed in very weird ways with spatial coordinates. This is just saying that being really careful about our parameterization in general relativity in terms of some invariant quantity tau, due to these conditions and restrictions, we end up with the result that we can get away perfectly well with parameterizing things in terms of time t instead of proper time tau. But we know that when we do Newtonian gravity, we just use time. We don't use tau. So that's all this condition is telling us. Okay? Now we turn to a spatial component. And for a spatial component, we now have that d2 xi dt squared. I can just replace tau with t now. Minus 1/2 eta I lambda d lambda h00 dt d tau squared is equal to 0. Okay. What is the first term? That's acceleration, exactly. That is the ith component of the spatial acceleration. Okay. The last part, again, what does lambda have to be? It has to be I. I is fixed in this expression, mu equals I. So this requires lambda to be I. That makes this into an I. And so this is going to become, at the end of the day, minus 1/2 di of h00. Okay.
What about the dt d tau squared?
So we're going to take an identification of t with tau, which is a possibility. I could use another linear combination, but that's just going to make things more complicated than they need to be. So dt d tau is going to be 1. Okay, so at the end of the day, this tells me that ai is equal to minus 1/2 di h00, or it's equal to minus 1/2 myself.
Positive?
Okay. No, hold on. Pause. Minus di minus, yeah, I meant positive. Okay. You'll understand why I wrote a negative in just a second. God almighty. 1/2 h00. There you go. So my indices are all over the place. Why do I have an upper and a lower index? Oh, because this is upper. Which it shouldn't be, which is making me nervous. But it's spatial. It's spatial, so spatial doesn't care if I have the index up or down. Okay. Okay, and I'll explain what that means in just a second. Why in the world did I write it like this? Why did I put the minus and the two minuses and thing in the parentheses and all that crap? What are we trying to derive? This. So what this is telling me is that I need to identify this quantity with the gravitational potential phi. Now that seems like, oh, you just picked that to get the right answer. Which you're right. Oh my God, we're never going to be able to do this. The only difference though is that that same potential appears here in an equation we're going to try and get from here. And it's going to turn out that the same assignment of phi equals minus 1/2 h00 gets me to this equation from this equation. So yeah, at a certain point we do have to identify where in the story we identify what the gravitational potential is for the Newtonian case. It's determined in terms of the time-time component in the metric fluctuation. But at least once we identify that, the entire rest of the story is consistent. Okay? All right, so here's what I'm going to do. I'm going to continue and finish doing A, and of course we're going to record it. If you need to go, go. It's going to take about 10 minutes. But I need to get through this because I kind of have to move on to the next topic after the exam. So this will take about 10 minutes. If you're going to leave, just leave quietly, but I'll try and scoot through this as quick as I can. Okay. And the reason why, and you might have realized this, the reason why this is looking a little wonky in terms of up indices and down indices is this equation itself is a bit wonky. Because acceleration we normally think of as a vector, but the divergence del, or the del operator, the gradient, sorry, is normally a dual vector. So writing the equation in this way is already giving me sort of a mismatch between upper and lower indices. It doesn't matter if things are purely spatial. Okay? But if you try and take it to 4 dimensions, that's where you'll get screwed up. Okay, so very quickly, I'm going to go back and get A out of this, and then send you on your way. And I swear to God, this is the last topic that I'll have to rush like this. Okay, so now for A, we want to get del squared phi is 4 pi g rho from Einstein's equation. So what we're going to do to get started is we're actually going to rewrite Einstein's equation in what will prove to be a pretty useful way. And this is what's called the trace reverse form. And this is something that we'll actually use when we're looking for solutions. So if I take Einstein's equations and I literally just hit it with the factor of the metric, on both sides, then you'll notice something magical happens. What is g mu nu r mu nu? It's r. This gives you the Ricci scalar. Okay. What is g mu nu g mu nu? Say it again. It's 4. Yeah, all of the indices here are contracted here. If you just contract 2 of them, you get the identity, but then you're contracting, and so you're summing over the diagonals of the identity. So this gives me 4, which cancels this 2, so this gives me minus 2r. I know. And then the right-hand side is just the trace of the energy momentum tensor. Okay? So at the end of the day, we can say that r is equal to minus 8 pi g times the trace of the energy momentum tensor. That's just solving this for r. And what this means is I can take this expression for r and plug it back into Einstein's equation there, and then move the t terms to one side. And so I end up with an expression of the following form. R mu nu is equal to 8 pi g T mu nu minus 1/2 G mu nu T. Okay, so this is Einstein's equation in trace reverse form. That is going to be useful later on, and I'm just going to go ahead and tell you why, because we're going to solve Einstein's equation in a vacuum. And in a vacuum, the energy momentum tensor is 0. And when you write Einstein's equation in this form, the entire right-hand side vanishes, and it reduces to just r mu nu equals 0. Magically, that's the same equation as r mu nu minus 1/2 G mu nu r equals 0. It's just not obvious. Okay, so now we've got Einstein's equations in trace reverse form. We need to specify a source. That is, I need to tell you what is the T mu nu we're going to use. What is going to contribute to the Newtonian gravitational field as a source?
The mass of the particle.
You're joking. Say it again.
Just the density.
The mass density. I mean, it would be the mass of a particle if you had one there, but we're generally thinking of large systems, so the mass density. So that means that our energy momentum tensor we can write in this form as the mass density in the upper left term and then 0 everywhere else. So that means that T00 equals rho, T mu nu equals 0 for mu or nu not equal to 0.
Why not just say Tij?
No, because you can say T0I is 0. It doesn't matter. I'm not going to worry about this. The only non-zero component is T00. That's the important thing. Okay? Okay, so if we want to form the trace, because the trace of T is what goes in here, then we have to say T is G mu nu T mu nu. Okay, which you would think would be simple, except we've got this stupid inverse metric. Okay, but plugging that in, let me get rid of this nice little rim. Plugging this in, eta, whoops, eta mu nu minus eta mu alpha, eta mu beta, h alpha beta T mu nu. Okay. The only non-zero component is the 0,0 component here. And so that means that the only components I should be considering on this term for mu and nu is 0,0. So this is going to be eta 0,0 minus eta 0 alpha, eta 0 beta, h alpha beta T 0,0. Talk about getting a lot of mileage out of something. What does alpha and beta have to be? They have to be 0 because the metric and its inverse are diagonal. So we only look at the alpha beta equals 0 terms. So I can erase the alpha beta there and make them zeros. Okay. What is eta 0,0 inverse? Or is eta inverse 0,0? Say it again.
-1.
It's -1, so this is -1, -1, -1, okay? So T is just going to be 1 plus, or -1 plus H, -1 minus H00, T00, or -1 plus H00, T00. Okay? All right, so now we can write the right-hand side of this equation. And I'm just going to focus on the 0,0 term here because that's the only one that's getting a non-zero contribution from the first term. So we have T00 minus 1/2 G00T. Say right-hand side. And let's see. So plugging everything in. 8 pi g rho minus 1/2 G00 is G00. -1 plus h00. I know it's complicated, and then we just did our expression for t. So I'll let the minus there cancel with the minus there, plus 1 plus h00, t00, but t00 is rho. That t00 is rho, and I think that's it. Okay. When I multiply this bad boy out, I'm going to have some h00 squared terms. Okay. And my cross terms will vanish because I got a minus, got a difference in the sum. So at the end of the day, multiplying all this out and adding it all together, I get 4 pi g rho. That's literally arithmetic at that point, which is what we're looking for the right-hand side. Now to finish up, we just got to do the left-hand side. The left-hand side is, of course, the Ricci tensor. And so banging this out, we only want to look at the 0,0 component of it. So remember the 0,0 component the 0,0 component of the Ricci tensor comes from the Riemann tensor in that way. Okay, the Ricci tensor in general comes from the Riemann tensor where I contract the upper index with the middle of the lower indices. We talked about that last time. So if I'm looking for 0,0 here, I just take this and put 0,0 there. Okay, I've got to dig into this expression because I've got to ultimately relate this to the metric. Okay, and then we can express the Riemann tensor in terms of what we looked at last time, which is derivatives of the Christoffel symbols and quadratics in the Christoffel symbols. So it's kind of an index nightmare, but it's okay. We've seen worse. So if you actually took your definition of the Riemann curvature tensor that we saw last time in terms of the Christoffel symbols and their derivatives, actually we saw it the time before last, I think, and then just plug in 0,0 everywhere, you'll get something that looks like that. Okay? And then here's the good stuff. These are all quadratics. Okay, so first of all, the Christoffel symbols depend on the derivatives of the metric. Okay? So if I'm looking at quadratics in the Christoffel symbols, then I'm looking at quadratics in the derivative of the metric. So these are going to be higher order terms that I can ignore. Nothing in the story depends on time. So the Christoffel symbols won't depend on time. So the time derivative of the Christoffel symbols is 0. So the only term that survives is this one. But now, of course, we have to blow up the Christoffel symbol because it's given by a big expression. But it's not that bad. We're almost there. So blowing up the Christoffel symbol, well, actually, before we even blow up the Christoffel symbol, let's do the sum. So this sum is going to include this term. Okay, this is the sum over all lambdas. It's going to have the lambda equals 0 contribution, and then the spatial contributions. What is this term? This is 0. Okay. So now let's blow up the spatial Christoffel symbol. Oh my dear sweet God. Okay, so we're so close. We're like right there. And you are such troopers for hanging in there. Okay, so the Christoffel symbol is 1/2 g I lambda, and I'm putting in the specific index values that are associated with this particular assignment. So remember, you take the general form of this And you just say, okay, I want mu to be I, a spatial index, I want nu to be 0, lambda equals 0. You use that definition and you'll bang out this expression. Hey, look, man, we're getting some serious mileage out of this. What's that? What's that? Damn, this is so easy. Can teach this in physics 1 tomorrow. And so at the end of the day, this term vanished, so this thing is going to become partial I of 1/2 gi lambda of minus d lambda, so let me just pull out a roll minus sign, of d lambda g0, 0. Snap, look at that. What does lambda have to be? Lambda has to be I, otherwise this is going to be 0. So that just gets replaced by an I. God, this sucks. Listen. Okay. And here, I'll just come over here, finish the story. So at the end of the day, I can, if I want, just use this GII to raise this I and make it an I up here. So I can say that the left-hand side is equal to minus partial I 1/2 partial upper I of G0, 0. Okay, I could plug in the actual form of GII, but I could just instead just raise this index, because that's what GII does. It raises the index. Okay, what is G0, 0? Yeah, G0, 0 is eta 0, 0 plus h0, 0. So this is minus 1 plus h0, 0. This is the derivative of it. So the derivative of minus 1 is just going to disappear. So at the end of the day, this becomes minus, or let's just say the derivative I of the derivative of I of minus 1/2 h0, 0. See it?
Yeah.
There it is. We replace minus 1/2 h0, 0 with phi, and that guy just becomes del squared phi. The exact same replacement that we had to use to get the geodesic equation down to Newton's law. So there's two takeaways from this. One that we will use and one that I think is just important. One is when we're doing general relativity and looking for solutions, at some point or at various points we will make that identification. So I'm going to at various points go, remember when we set the minus 1/2 the time component of the metric to phi? Well, that's where we're going to do it. The second thing is, I started this semester off asking you, what does general relativity generalize? And of course, many people say it generalizes special relativity because it's called general relativity. But it's not. It's a generalization of Newtonian gravity, but also it's a generalization of any physics on curved space-time. So it's a generalization of electromagnetism, all of the standard model, and so forth. But in terms of just the gravitational side of the story, you need to be able to reproduce Newtonian gravitational force laws and how the fields are determined from sources, and then also how those gravitational forces influence the motion of things. Okay. It's all contained in general relativity, but you see there's a very precarious set of limits that have to be taken, and that's because general relativity is a very, very big theory that includes a lot of effects. With special relativity, you just take one limit, right? You just take c to infinity. Here, we're effectively taking, well, we're taking 1 to infinity, but, you know, 1's a big number. We're taking c to infinity, but we also have to do a weak gravitational field limit. So, for example, I could take an object that's moving slowly. So this is maybe relevant. But if it's moving slowly near the singularity of a black hole, Newtonian gravity isn't going to work because you're dealing with very strong gravitational fields. Okay? Or if I'm considering, some binary collapse, two black holes are collapsing or two neutron stars or whatever, then I'm definitely not going to be working in the static limit. And so I don't expect Newtonian gravity to be a decent approximation to that at all. Okay? All right, thanks for hanging in there. Well, I'll see you on Tuesday. Exam in hand. I'll be here Monday night to answer your questions and give you assistance as needed. It's like nothing. You guys love me or hate me.